Okay, so here's what we were talking about last time. We were doing directional derivatives, and here's the picture. And we have a formula here for the the definition of a directional derivative. But just a reminder, the picture, the idea, the reason we care about that formula is because it allows us to associate, wherever we might happen to be, whatever point, there's the corresponding output value. Whatever velocity we might be moving with in the domain, the formula above computes the corresponding output velocity. So the directional derivative, this directional derivative formula here, computes the output velocity corresponding to a given input velocity. Now I'll remind you that this is the perspective that we want to take on derivatives. We want to think of derivatives, forget about slopes for now. We'll come back to that later, a little later today actually. But primarily, the cornerstone point of view on derivatives to be that there's we're interested in a relationship between input vectors and output vectors. So given an input velocity, what's the corresponding output velocity? Or given an input displacement, right? What's the corresponding linear estimate of the corresponding output displacement? Okay, so there's that. The term we use is directional derivatives. Now, I do want to talk a little bit about the term directional derivative. It does not mean the same thing to everyone, unfortunately. There's a little bit of multiple usages, let's call them, of this term. So I like the term directional derivative as I've defined it here. Right? No surprise. But let me tell you what the other point of view is. The other point of view is to say, okay, well, directional derivative. The base of the word here is direction, and we've already talked about how, well, very naturally, we express directions with unit vectors. So in a lot of books, this formula here, same formula or equivalent formula, but they will say the term, a directional derivative of a function at a point. With velocity that is a unit vector, and they restrict the formula. Same formula, right? Same notation, probably. But they will restrict the definition to applying only to unit vectors. And it turns out there's some nice things that you can say, if the velocity is a unit vector. So there's a point of view there, and there's a whole section of my book here talking about what I like to call unit directional derivatives. But note that in this book I'm using the term more generally for v to be any velocity vector. And again, I think it's a really natural concept. You have an input vector. What is the corresponding output vector? Okay, so heads up though, out in the real world, if you hear someone say the term directional derivative, you have to okay, wait a minute. Which one do they mean? Do they mean directional derivative defined in this sense, or do they mean directional derivative are they assuming that I understand that they meant that the input vector has to be a unit vector? And you have to clarify. Okay, we'll have much more to say about that in a few minutes. Okay, so we already did this example here. I'm going to proceed along now with the next example. And here's our function. I'm going to take a directional derivative of this function here. So let's see here. We have, you'll notice, a starting point. We have a velocity given to us. So we're in the domain in R3. We're at this point moving with this velocity. And the question is, the output in the target, this output's going to be moving, what's its velocity? And of course we know directional derivative is the answer to that question, so we're just going to compute the directional derivative. Here it is. Right, straight from the definition. Now this is another plug and chug calculation, so we're just going to go straight into it here. Our starting point, 1, 2, 0, is there. The velocity that we're moving with, v, 213 is there. So notice I'm generating a parametric curve that literally starts at this point, moves with that velocity as described. Right? Then in purple here, this is our input parametric curve that I'm then plugging into the function. Right? So after I take f of it, that then is the output parametric curve. So let's do that calculation. How do I put this into the function f? Well, keep in mind that what I'm plugging into the function f has these coordinates. Right? These are x, y, and z. I'll plug those straight into my function. Now let's come up here and notice what our function is. Our function is xy is the first coordinate, and then yz is the second coordinate. So the x, y, and z that I'm plugging in, I've got to multiply x times y and then y times z. Okay, so let's come down here. Here it is. The function. Right, and notice that's what it is, x times y, right here in the first entry, then y times z, right here in the second entry. Okay, a little bit of algebra, multiply all that out. You guys can do that. Now, this is our output parametric curve then, okay, which we're then taking a derivative of. That's just a little bit of calculus. That gives you this as the derivative, and of course we plug in t equals 0 after having taken the derivative. Plug in t equals 0, and there's your answer, 5,6. Okay, now let's summarize. What does that mean? Coming back up here to the statement of the question, we have a function from R3 to R2. Here's our R3, and here's our R2. Right, we were given that we were starting at this point and moving with that velocity in the domain. So we were at a point like that, moving with some velocity. And we have successfully computed in the output, its image is at that point and moving with, well, some velocity. And notice we get a vector, right? Well, we better get a vector. We're looking for the velocity in R2. We have our target is R2. The outputs from this function land in R2. I have values in R2 that are moving around. How does something move in R2? What is the velocity of a point moving around in R2? It better be a two-dimensional vector. And of course it is. Okay. All right. There's another example here I'm going to let y'all read on your own. It's very analogous. The last observation I want to make is how directional derivatives are computed component-wise. We talked about component-wise computations. Directional derivatives are also computed component-wise. Now, this is actually not that big of a surprise. If you think about it, if you look at the definition of a directional derivative, the derivative of a parametric curve. Now, we form a special, particular parametric curve with the points A and B and the function f all in mind. But it goes into generating a parametric curve. We're computing here the derivative of a parametric curve. Derivatives of parametric curves we already know are computed component-wise. This being just an example of that, of course, it is also computed component-wise. Okay. All right. So what that means is you come back to this example that we just did. If we had looked at two separate functions, suppose we had looked at this function that I'm going to call f1 from R3 to R1, defined by f1 of xyz equals xy. So just that first component. If I were to compute the directional derivative at this point with that velocity, directional derivative of this component function, xy, being as it is the first component of the function I just computed, if I were to go through and compute this directional derivative, I would get just, well, the first component of this output directional derivative. I would get just 5. And I would encourage y'all to go through that calculation just as a sanity check. So do this one, right? Write down this function, take this point A, this velocity V, plug it all in, and confirm that you get 5. And in fact, notice what you will notice when you do that is that the calculation that you're doing, you will in fact be generating the exact same input parametric curve. And for the output, well, you won't have the whole f. You'll have, though, exactly the first component. So you'll recognize along the way, same input parametric curve, and highlighted in blue here, the same first components in that calculation. So anyway, give that a shot. Confirm that it works as you would expect. Okay, so moving along now, I'm going to talk about unit directional derivatives. Let me remind you, I made a vague reference to this a couple minutes ago. We were talking about terminology, and again, tragically, the term directional derivative means different things to different people. It's unfortunate. Anyway, in this book, directional derivative is intended to be a general term. The input velocity could be any velocity. It's certainly a useful construction. And I need to have a term in which to describe for that useful construction. Now, let's consider, though, what happens when our input velocity is a unit vector. Turns out something really nice happens. I'm going to segue into this by doing an observation. Let me zoom in one notch. Here we go. I'm going to start off by observing that directional derivatives have this lovely property of being what I call the scalar multiplicative. Let me get that on the screen. Yeah, here we go. Scalar multiplicative. So what do I mean by scalar multiplicative? Well, what I mean is that if your input velocity has a scalar factor in it, you can pull that scalar outside of the vector. Right, so inside of your velocity, if there's a scalar factor of k, you just pull it right on out of there and put that scalar k outside of the direction. Okay. Let's sanity check. I mean, well, let's think about, why is this physically plausible? Well, notice both of these questions say, I want to compute how fast the function is f is changing. We're starting at the same base point a. We're looking at the same function f. And we're going in the same direction. Right here we're going velocity v. Here we're going with velocity kv. They point the same way. So not only are we starting at the same point, but we're moving over the same turf in the domain of f. The only difference is that here on the left side we're going k times as fast through that domain of the function f. We're going across the exact same values, k times as fast. No surprise that the function's output changes k times as fast. It's kind of exactly what you would expect to be true. Okay, let's prove it though, just to be sure. It's a very straightforward calculation. I'm going to take the left-hand side and just compute straight out. Right. There's the definition of directional derivative. It's just a recopy. Notice that my velocity vector here, kv. Okay. Clever move, as it turns out, is to take this pair of factors, the t that represents our sense of time as we're taking this derivative, and the k, that's the factor that we're going to want to pull out, rewrite those as s. So, thus giving us that. Right? And ends up being a convenient move. And then what we're going to do is just apply the chain rule. So notice that here I have an expression that depends on s. S depends on t. We have a composition of functions. This is single variable composition of functions. So f is a function of s is a function of t. So I can compute the t derivative by first taking the derivative with respect to s and then multiplying by ds dt. It's just single variable calculus chain rule. Hope that's not a shocker to anybody. Having done that, s being tk, ds dt is equal to k. That's an easy one. And this, you'll notice, is exactly what it's supposed to be, the directional derivative with velocity v. So straight up calculation, we see that this works, and we can factor out scalars. Okay, who cares? Here's a nice application of that idea. Let's look at our typical scenario where we have a velocity vector v. Don't forget, we can always take any velocity vector v and view it as being a unit vector times a speed at a magnitude, I'll say. We're viewing v as a velocity, then this scalar is the speed. So we can think of it as a unit vector times a scalar. Doing that, here, let me do it like this. Interpreting that velocity vector here as having a scalar factor. We just agreed that you can pull scalar factors out. I'm going to pull out this scalar factor of little v. Like so. And so that velocity, pulling out the scalar factor of little v, and leaving in, of course, then the unit vector u. Okay, who cares about that? What does that buy for us? Well, quick observation. V being the magnitude of the velocity, right? The directional derivative being as it is the output velocity. Notice that this expression here, this directional derivative where u is a unit vector, the unit vector pointing in the same direction, this has a kind of a familiar feature that we kind of swept under the rug when we were talking about regular directional derivatives. Thinking about in single variable calculus, we were viewing the derivative as a factor. It was something that you multiply by an input velocity to get the output velocity. Directional derivatives were the output velocity. It wasn't something you multiply by an input velocity. It just is the output velocity on its own. Here, this thing is recovering that role of being a factor. This thing, this directional derivative with the understanding that u is a unit vector pointing in a given direction. You multiply it by input speed to get output velocity. So that's again, kind of a familiar concept, and therefore that makes this kind of a natural thing. Now, let me qualify that a little bit. You might have noticed my careful terminology there. We're not multiplying by input velocity to get output velocity. That's not a velocity. In green here, that's not a velocity. That's a speed. It's a magnitude of a velocity. So it's not exactly what happened in single variable calculus. Nevertheless, kind of a familiar construction. Okay, so that makes this a natural thing to want to talk about. It's a directional derivative, of course. It's a directional derivative, though, with the understanding that the base, that the input velocity, that u thing, has to be a unit vector, and thus I'm using the term here, unit directional derivative. Okay. Yeah? Everybody on board? Turns out that the unit directional derivatives do have some nice features. So, as we just discussed, the unit directional derivative is a factor. It's a factor that you multiply by input speed to get output velocity. Okay, fine. We already talked about that one. Likewise, I'll come up and talk about that picture in a moment. That unit directional derivative. I mean, we don't have to interpret our input as being a velocity. We can interpret our input as being a discrete jump, a discrete change in position. And so then the unit directional derivative is the thing you multiply by distance in the domain to get an approximation of distance to the target. Okay. Here's a picture. Talk about what's happening. So we found ourselves in this situation where we're moving with some input velocity. We want to know what is the corresponding output velocity. That is the directional derivative. Okay, but viewed differently, let's talk about this thing. That is the vector that you get by saying, okay, yeah, the velocity in the domain, okay, yeah, fine, but here's the unit vector indicating my direction. And in that direction, I can compute this unit directional derivative. So as I move in that direction, that's how fast in general the output values of the function are changing. And so then I simply can factor in that this magnitude is what you multiply here to get the actual output velocity. Okay. Here's a different way to think about it. And I'm going to come back down to this equation we were just looking at. We're just looking at this picture, this equation, excuse me. Thinking of this as a factor that you multiply by an input distance, right? Magnitude of displacement, so distance. Something you multiply by input distance to get an output change. Well, it almost leaps off the page. If you think about it, what this says is that this unit directional derivative is telling you change in the function per unit distance traveled in the domain in the given direction. So it's the rate of change of the function with respect to distance. You might even write it then as df ds. This is a common thing to write down. So duf df ds. How fast is this function changing per unit distance traveled? Now, why would we care about that? Why is this interesting? Well, it's actually fairly common that we want to know how much a function changes per unit distance and not how much does a function change per unit time. Here's an example. Suppose you're driving along a road, right? Now you have your own, again, I want to draw the distinction between the road and the road trip, right? So as you personally are driving along this road, you may experience a change in, let's say, the temperature, the ambient temperature as you drive, right? As you walk, whatever. You may experience, certain number of degrees per hour as you move, right? But that's you. You're driving fast, let's say, right? Someone else might be driving slow, right? Your own personal experience may be of great importance to you, but it is of no importance to other people, right? So if we want to talk about just intrinsic to the situation itself, I don't care about Bob as he's driving along and Bob's needs, and Bob can handle Bob's needs. I want to know at this location, as you're moving in that direction, how fast is temperature changing intrinsically, right? So per unit distance travel, per mile as you move in a certain direction, right? How many degrees per mile? And then Bob will take that information and say, I'm going 60 miles an hour, so compute, that's how fast I'm experiencing it. Someone else will say, I'm driving 42 miles an hour. They can similarly multiply by their speed and compute their experience. But the thing that's intrinsic to the situation is the rate of change with respect to distance. So unit directional derivatives give you that, right? Change per unit distance. Okay, so that's nice. Here's a related point. If you are looking at a graph, now y'all know I have to put in my usual disclaimer. Very often we're not looking at a graph. Please don't just assume any picture you see is a graph. Lots of pictures are not graphs. But if you are looking at a graph, right, then the unit directional derivative does have a nice interpretation in that context. The unit directional derivative is the slope of the tangent line to the curve that's a cross section of the graph in that direction. And that's super familiar, right? Thinking back to single variable calculus, again, everybody's knee-jerk favorite point of view on derivatives. Well, that's the slope of the graph. Well, unit directional derivatives are the slope of the graph in the certain direction that's given. So let's look at this picture. Here's a picture. Now, what I have here, I'm drawing a picture of a function. Let's see, can I fit the? There we go. We're looking at a function f from R2 to R1. All right, so our domain is, you might say, represented by the xy plane down here. The target is represented by height. This being a function from R2 to R1, the graph is a surface. Right, so we have this surface, and we ask the question, what does this thing mean, unit directional derivative? Well, don't forget, this A represents a point in the domain. U represents a unit vector giving you a direction from A in the domain. All of this stuff here is in the domain. Wrong color. U and A are in the domain. There's A, there's U. Right? And what this says then is, as if you're at that point moving in that direction, thus defining this that plane. Okay, fine. That plane. If you look at the cross section inside of this plane, cross section of that graph, the cross section is going to give you this curve. That curve has a certain tangent vector. Tangent line. The unit directional derivative is the slope of that tangent line. So it's the slope of, sloppily people will say it's the slope of the graph. Obviously it's the slope of the tangent line to the graph. But again, you have to asterisk it even more. Not just any tangent line. There's lots of tangent lines in different directions, right? Specifically, Specifically, it's the tangent line that comes from the plane, the vertical plane that's defined by the direction you're actually going. That's it. Very familiar, right? This really smacks of single variable calculus derivatives. Everybody on board? Questions? Okay. All right. By the way, this is not hard to show. It's a nice exercise, even, you might say, to show that if you think about how would you compute the slope of that tangent line, just bluntly, brute force, directly, how would you compute that slope? Think about it as a limit, right? You're computing, just like in single variable calculus, as, let's say as t approaches 0 or h approaches 0, a plus tu and the usual, and think about these points kind of getting closer and closer, and secant line, and just do the usual calculation. What you'll find is you end up with an expression that's equivalent to unit directional derivative. Okay. Alrighty, so we have these two equivalent expressions then. Right, in fact, I'll zoom in a little bit here. So if you want to know how fast the output values of a function are changing, you have a couple options. One is you can just compute the directional derivative straight out. Right, boom, just like in the last section. No problem. Yeah, there's possibly some problem, but anyway, this is certainly an approach that you can take. Now, your alternative is take your velocity vector, factor out the magnitude, the speed, replace then as your velocity just the unit vector in the direction you're going, compute the unit directional derivative, and then multiply by the speed. So, which one's better? And the answer is neither necessarily. There are some circumstances in which it just makes loads more sense to compute this thing, right? And there are some situations in which it makes loads more sense to compute this thing. So I'm going to show you a couple of examples. Please don't make the mistake. A lot of students make the mistake of thinking, okay, well, unit directional derivative came after in the textbook, so it must be the more modern, better. It's not this outdated, section 5.3 method. This is the more updated 5.4. Why do I keep saying 5? We're in chapter 4 now. This is not the outdated 4.3 method. This is the modern, more sophisticated 4.4 method. And that's just not true. It's just different. Right? It has its uses. It depends on the situation. Okay, so let's see some examples. So we're in a forest. Positions given by coordinates x and y, the usual way of keeping track of where you are. And we're worried about mosquitoes. as I always am when I'm in a forest walking around. They love me. I do not love them. So here is a function representing the concentration of mosquitoes. Now I've made up this function here, and I did so with the idea in mind that it's a decaying exponential centered at a particular location. So there's some swampy bog at some point in the forest, and X and Y, I guess the swampy bog is at the origin, and the further you get away from the swampy bog, the fewer mosquitoes there are, but as you get closer to the swampy bog, there's lots of mosquitoes. This function kind of does that. Okay, so let's suppose that you are at this point, and you're moving, with that velocity. So we have an A, we have a V. What's the rate of change of this function? How fast? Very relevant question, by the way. How fast is my mosquito experience going down? You're going to want to know that. Okay. Okay, so we want to know df dt. We could compute the directional derivative, right? The directional derivative is what we're interested in. Let's see here. Well, let me write this down first. Where this v is the given velocity. That's what we want to know. You'll notice that instead I'm doing the calculation from a unit directional derivative point of view, so I'm factoring out the speed, and I'm going to use just a unit vector pointing in the given direction, do the calculation that way. Let's see how this plays out. Notice that your A plus TV, so your A is the point 2, 1. TU, well, you're going to get a minus T in the first coordinate, nothing in the second coordinate because of what the U vector is. Okay. And now it's just a little pluggy-chuggy calculation. I'm going to let you guys work out the details, but notice your X and your Y have relatively simple formulas, right? X is just 2 minus T. Y is 1. That's very convenient. So this, plugging into the function, come out, you get this quadratic exponential, you multiply. You got to take some derivatives. You got to fiddle with the function at that point. Okay. And it's fine. This factor of v just sits along for the ride, comes all the way down. So what if I had done this the other way? If I had put the velocity in there instead of the unit vector, then instead of having 2, 1 plus t negative 1, 0, instead of having that, which gave me that, I would instead have this 3.5. Right, this this 3.5 right here would have been inside of there. Right? So I would have had a fraction in my formula for x that would then make fractions go all the way through this calculation. Not that it's not doable, but it's slightly less desirable to have to deal with fractions as you're doing non-trivial algebra. Right? So all else being equal, I think it's a slicker move to don't do that, but just have that, the inconvenient little fraction 3.5, have it sit off to the side by itself and not work its way all the way through your algebra. I'm going to call this a win using the directional derivative, the unit directional derivative. Is everybody on board? All right. So here's another scenario. We are looking at the graph of a certain function f. Right now, key word, graph. This is a graph. Right, so you get to think of it in the way that you're accustomed to thinking of what functions look like. So it's a graph. We are walking around. We have an ant here that's walking around, and he's sitting above the point 2, 0 on the graph. And the question is, if he starts walking in a certain direction, what's the slope of his path? All right, now the question has asked for the slope of a graph. Slope of a graph. Well, that's unit directional derivative. We already know, right? So it's not asking how fast is altitude changing per unit time. It's not asking about the ant's experience of altitude change. It's asking about what is the nature of the graph in a certain direction, but with no comment on speeds. So this is a question about road, not road trip. And the answer is unit directional derivative. Okay. So we don't immediately want to compute directional derivative. In the last question, the unit directional derivative was easier to compute. So there's a temptation to say, hey, cool, let's just compute the unit directional derivative. That's what we want anyway. Isn't it going to be easier to calculate? Why don't I just do that? I'll make the observation. Here it kind of goes the other way around. Our velocity vector is pretty easy to write down. The unit vector, though, is not. Here the unit vector, taking this 1, 1, turning it into a unit vector, getting u equals, this thing here. Now we've got fractions and square roots that popped up. So, it's just not always the case. In fact, one could argue it's often, I don't want to say usually, but it's often not the case that the unit directional derivative is easier. Often, the unit directional derivative is harder to compute. Right, so what I'm going to do in this case, keep in mind my goal was to compute the unit directional derivative, and I'm going to do it sort of the opposite way. I'm going to compute the unit directional derivative by instead giving myself the convenience of computing the directional derivative directly, and then dividing by the square root of 2 per this formula. So u being v divided by the square root of 2. Everybody see what I did there? Okay, now again, details, not that bad. Again, v having been easy to write down, I get an easy input parametric curve and the algebra works out nicely. Okay, so always think it through. This next example I want to do, I'm not going to go through details. I just want to point out that if you just reflexively go with unit directional derivatives, in some cases you're going to do completely unnecessary arithmetic gymnastics that accomplish nothing. Right? So let's consider this scenario where you're interested in, you wish to compute the directional derivative. Got a velocity vector given to you, 2, 7. Plan A could be, take the 2, 7 and play the game. Do your thing. And notice your coordinates are integers. It's nice. Okay. The alternative calculation, instead of computing directly, if instead you computed the magnitude of v and multiply that by the directional derivative, unit directional derivative using the unit vector. Don't forget the unit vector is v divided by the magnitude of v. Notice what you've given yourself is a situation where you have to compute the magnitude of this vector for one thing to get your unit vector. That's going to make this calculation here is going to be more awkward because you've got fractions and square roots. Right, square root of 53. The square root of 53 is going to be all over this calculation, at the end of which you're then just going to multiply by the square root of 53. And what's the point, right? Why would you bother? You can see right here that these are going to cancel. Why would you do that to yourself? Right? Go through and have square root of 53s everywhere if you know they're going to cancel out. In this case, it makes no sense at all to use unit directional derivatives. Everybody on board? Yeah.
So even though it doesn't seem to be multiplied, but we can still cancel it.
Well, so what I'm doing, what I'm using here is, you might remember the first thing we talked about in this section was how scalars will factor out of the velocity, right? So I'm taking this scalar factor of 1 over the magnitude, I'm pulling it out and then canceling.
Okay.
Yeah. Yeah, that's great. It's a very good concern, and you got to be careful about that kind of thing, about canceling things that don't really cancel. So I'm glad you were concerned about that. Yeah. Anybody else? Okay, moving along. Partial derivatives. It's another special case. Partial derivatives are directional derivatives, just like unit directional derivatives are directional derivatives. In fact, this is a special case of that special case. A partial derivative is a special case of the unit directional derivative, which itself was a special case of the general directional derivative. All right, so the special case here is that not only do we require that the magnitude be 1, but furthermore we require that that unit vector has to be a standard basis vector. And recall we talked about standard basis vectors. These are unit vectors pointing in the direction of the axes, right? So they're pointing exactly along either the x, y, or z axis, or however many axes you have. In terms of coordinates, the standard basis vectors are mostly zeros with a 1 in a single position. Okay, so turns out this is a really interesting special case. If you're looking at a directional derivative, and if your velocity is a standard basis vector, something wonderful happens. Let me show you what that thing is. It's very nice. Here's the calculation. There's your definition of directional derivative. Notice that as discussed, our velocity vector here, standard basis vector EI. So there it is, EI. Let me write down this derivative. That's how you compute a derivative. Now, specifically, this is a derivative where s is equal to 0. Right? And this is just a definition of a derivative. Derivative is a certain limit. All right. Now let's look at that limit. A plus h times EI. There's that right there. And then look here, the A is just, well, that's just whatever that is. And let's look carefully at this EI vector. The EI vector, don't forget, is mostly zeros with a 1 in a single position. And so let's think about what's going on when we look at this numerator. The numerator, we're taking f of the nearby point minus f of the original point and subtracting. It's at calc 1, right? Single variable calculus idea. But notice what is so nice about this calculation. This expression simplifies super nicely because the vast majority of these terms, you're just adding 0 to them. Like what's happening to A1? A1, well, we're adding h times 0. In other words, we're adding 0. In other words, we're not changing it at all. Right? Likewise, A2 is not changing. A3 is not changing. Vast majority of these variables are not changing at all. There's really only one variable that's changing at all. That is the ith variable. It's changing by an amount h. All the other variables are fixed. Okay, why is that convenient? By the way, notice this expression. That's a calc 1 single variable derivative, right? Limit new value of f minus old value of f over h. This is straight out of calc 1, right? And notice that because there's only one variable that's actually changing, because all the other variables are staying constant, it's like we're treating this function f as a single variable function. It's like we're saying, okay, f is a function of these several different variables, but let's staple most of them down to the ground. These are not allowed to. A1 can't change, so I mean it's a variable only kind of, I don't know, philosophically or something, right? It's not changing. It's constant. We could treat it as a constant because it is a constant for the purposes of this calculation. Let's just pretend it's a constant. we're taking the derivative then of a function f of, I was going to say a function of several variables, but not really. Most of those variables are constants. We're going to treat them as constants. Really, it's just a function of this one variable. We're doing a single variable derivative here, literally. Everybody see the idea there? This is tremendously good news. So what that means is you can do these types of calculations really, really easily. So, for example, how would I take this derivative here? And I'm going to treat y as a constant. Let's just suppose, well, let me come back. Suppose we're taking this unit directional derivative in the E1 direction. In the E1 direction, x is the only thing that's changing. We're moving straight along the x-axis. Y is not changing at all. And if y is not changing, I'm going to treat y as a constant. As you move in the E1 direction, so again, let me highlight. So derivative with respect to x. Don't think of this as a multivariable calculus problem anymore. I'm taking an x derivative of x squared times a constant. Well, then I get 2x times that same constant. I mean, this is, calc 1, easy derivative. Next term, taking the x derivative of, there's a temptation to look at this y squared and think, multivariable calculus. Now, y is I'm moving in the E1 direction. Y is constant. It may be a bulky constant, but it's a constant, and the derivative of a constant is 0. That makes sense to everybody? This is how you compute partial derivatives. These are the world easiest derivatives to compute. Let me give you one more example. This is going to seem really, really wrong when I write this down, but this totally works. Suppose we wanted to take the derivative. Let me write this out. I'm going to say E1 direction of, let's have our function be x squared plus 1 to the power of y squared plus 3. Y'all remember logarithmic differentiation? If you have a function to the power of a function, there's a method from single variable calculus, Calc 1, for taking the derivative. It involves using, you take the log of both sides of the equation and you use log property. It's very clever. If you have an expression like this where you have a function to the power of a function, it's a necessity. And so you look at this and you're thinking, okay, this is going to be one of those logarithmic differentiation things. But it's not. Because what we have here, we're taking the derivative in the E1 direction. That means we're taking a partial derivative with respect to x. X is the only variable that's changing. The other variable, y, is constant. So what we have here is x squared plus 1 to the power of a constant. And you take the derivative in the usual way. I'm going to say here d by dx of x squared plus 1 to the y squared plus 3. And so y squared plus 3, x squared plus 1 to the power of y squared plus 2. And your fur is going to crawl when you write this down, because it seems like, you can't just play the, x to the n, get, the power rule, plain old power rule, when this is a function. It feels like this is a function. This seems really, really wrong. But it's not. That's fine. It's a constant, and you treat it like a constant. And then, of course, let's not forget the chain rule. Factor of 2x. But this is fine. Everybody happy? So the way I like to say this, by the way, is that partial derivatives, not only are they easy to compute, I would argue partial derivatives are even easier to compute than Calc 1 regular plain old derivatives. Because when you're looking at a Calc 1 plain old derivative, everything that you got all this stuff and you got to go through and apply the rules. When you're doing partial derivatives, you get to first look at your function and say, oh, this whole complicating section of it, I'm just going to pretend that that's a constant. Right? You get to pretend that large tracts of the expression you're interested in are constants, and then apply exactly the same rules. Arguably easier than single variable derivatives. Okay. All right. Notation. So here's our expression. This is don't forget this. Ultimately, what we're computing when we compute a partial derivative is a directional derivative. It's a directional derivative where your velocity is a standard basis vector. So this notation is fine. But a more common and convenient notation is to write it like that. Note this symbol here. That's not a D. Looks a lot like a D. It's not a D. It's also not a delta. A lot of students mistakenly think, oh, it's a funny looking kind of lowercase d-like little symbol, must be delta, but it's not. It's not D. It's not delta. Notice that the delta kind of flops over to the right. This does not. Right? It's just, it's like a backwards 6, you might say. Right? Anyway, it's the partial symbol. So this gets pronounced when you're if you're looking at this expression here. You can say the partial of f with respect to xi. A lot of times people will abbreviate that to partial f, partial xi. Totally fine. But very important, don't use a d. If you write a d, it's kind of wrong. Ultimately, despite the fact that we're treating these functions as being single variable functions, this function f is in fact a multivariable function, right? And so when you say I want to take a derivative with respect to xi, you need an acknowledgement that this is not quite exactly Calc 1. We do have to say, and I am going to hold these other variables constant when I take this derivative. Right? There are other situations where you might not necessarily do that. So in order to make it particularly clear that we're talking about a partial derivative, make sure you use the partial symbol. Okay. All right. Okay, another handy notation for the partial derivative. This is kind of what you might call a Newton-like notation. The fraction-looking notation over here is looks a lot like the Leibniz notation for derivatives. Right? It looks a lot like df dx. It's not the same, of course, but it looks a lot like that. This is kind of more smacks of f prime. Now, don't forget, if f is a function of several variables, then you have to say derivative with respect to what? With respect to which variables? So you can't just say f prime. That wouldn't make sense here. There's several different input variables. But having a subscript of x instead of a superscript of a prime kind of serves that role. Right? So this is the most Newton-like notation that we have for partial derivatives. Okay, and along those same lines, again, if you've given a name to the output variable, you might then alternatively say z sub x if z is the name you've given to the output value. So in some situations that's actually very convenient. Okay. Computed component-wise, well, of course it is. Let's think through why is it. Why is it that partial derivatives are computed component-wise? Well, partial derivatives are directional derivatives. Directional derivatives are derivatives of parametric curves, and we established a while ago that derivatives of parametric curves are computed component-wise. So it's super news. It's exactly what you would hope. Fingers crossed is the case. It's exactly what you would expect, and it's also true. Okay, so because this is a special case of previous constructions, all those interpretations come along. So partial derivatives being as they are unit directional derivatives, are factors. It's what you multiply by input speed to get output velocity. Right? What you multiply by input distance change to get expected output change. Okay. It's a slope of a graph. No surprise, it is a unit directional derivative. Unit directional derivatives are slopes of graphs. So partial derivatives give you slopes of tangent lines to graphs in the direction that you're going. But of course now, being a partial derivative, it is a direction that's along an axis. So again, slope of a graph, appropriately interpreted. Okay. All right. So let's do one. Okay, so we got this function f. We want to look at the graph of f. That's a surface. Okay, we've got this surface. It's the graph of f. I now want to take a cross-section, a particular cross-section of this graph. Now, this is a vertical cross-section in the x direction, not the y direction. In the x direction. I take a vertical cross-section in that direction. I'm looking at a graph of my function, taking that graph, want to look at the cross-section that's going to give me a curve, and I want to know the slope of the tangent line of that curve. Okay, we already know what the answer to this question is. If you are interested in a slope of a tangent line to a cross-section of a graph of a function, there's a lot of language there, right? Okay, if you're interested in the slope of a graph, just to kind of whittle it down a little bit. Slope of a graph. Unit directional derivative. So we know we want to compute the unit directional derivative here. Now, in what direction? Well, we're going exactly in the direction of the x-axis. That means that the unit directional derivative that I'm computing is a unit directional derivative where my u is E1. I'm going in the x direction. And that means that I'm computing the partial of f with respect to x. And so now it's just the mechanics of computing that partial derivative. I get to look at this function. I get to pretend that x is the only variable. Right? By the way, heads up, do pay very careful attention to what variable you are taking the partial with respect to. You got to choose the correct variable to be constant, or the correct variables to be constant. So here it is y that you get to pretend is a constant, not x. X is the variable because we're moving in the x direction. Okay, and this, let's see, let me zoom. This expression, ugly though it looks, x is the only actual variable. We treat y as a constant. This entire term here, e to the power of sine of y squared, there's no x's in it. Therefore, this whole term is constant, and the derivative is super easy to compute. Okay. Everybody all right? Okay. All right, let's look at this next question. Got a bird flying through the air. At some particular moment, we're at this point A, moving with velocity v. We want to compute the rate of change of this function h. Oh, excuse me. It's I'm sorry. That's the humidity, but the function's called f. I want to know the rate of change of that function f. So we want to compute a directional derivative. Right? Got a function, got an a, got a v, and you could just crank. You can say it's a directional derivative and just plug in and do it that way. But I'm going to save us a bunch of effort by taking advantage of a cool observation. First of all, the directional derivative that we're trying to compute, I can factor out the scalar. Right? If you look at that velocity vector v, 0, 5, 0, that 5 factors out really nicely, thus giving me a unit directional derivative. compute instead of a directional derivative, and furthermore a unit directional derivative where these numbers are nice. Right? E2, that's just zeros and ones. Much nicer. Well, anyway, a little bit nicer numbers than there's a 5 in here that would be getting in the way in our calculation otherwise. Second observation, though, because this is not just any old directional derivative, that's a unit directional derivative in a axis direction. That means it's a partial derivative. Right? So instead of brute forcing this and plugging in and taking a derivative of a complicated thing, I can just use Calc 1 rules. Right? I'm going to look at this expression here. It's a function of 3 variables, or so it would appear. Sine squared of, and I have x's, y's, and z's inside of here. But I'm moving in the y direction, only in the y direction. That means that x and z are constants. So I'm going to treat x and z as constants here. And the derivative of sine squared is 2 times sine. Chain rule tells me I have to multiply by cosine. And then chain rule again tells me I have to multiply by the derivative of with respect to y on the inside. That gives me that 2. That's just Calc 1. By the way, let me remind you, I am going to assume in this course that you're strong on all of your Calc 1, mechanics, how to use the chain rule and the quotient rule, the product rule, and blah, blah, blah. Integration by parts is going to start coming up when we get into Chapter 5. Substitution, integrals, this kind of thing. So make sure that you're good on stuff like this. Okay, so let's talk about second partials. The beginning of this is really just a straightforward observation. Think about second derivatives in single variable calculus. If you have a function and you take a derivative, the result is a function of which you can then take another derivative. Right? So same deal here. If you have a function from Rn to R1, so if you have a real valued expression with n different variables in it, and if you take a partial derivative, you get a real valued expression with n different variables in it. You can talk about the partial derivatives of the partial function just as well as you can talk about the partials of the original function. Okay. So, for example, that function there, f, you can take the x partial or the y partial, right? And either of those you could take partials of. So, partial of f with respect to x, you could take the x partial of it, or you could take the y partial of it. Right? And likewise, partial of f with respect to y, you could take the x partial of that y partial, or you could take the y partial of that y partial. And the rules are all the same, of course, it's the same partial derivatives, and so you get these different answers. A notational thing, just as a kind of a shortcut abbreviation. Heads up on this notation now. Look what I've done here. Here we have a partial with respect to x, and here I'm saying I want to take the partial with respect to y of that partial with respect to x. So note how I'm using the notation here. This is very analogous to notation in single variable. But combining these two seeming steps into one expression, you write it like this. And it's, I don't know, I kind of don't like it in a way, because I don't know. It's just cosmetically, it feels weird to say squared, because we're not really squaring. That's simple. It's not like we're multiplying it by itself, but it appears twice in succession, and so it's extremely common, and it's extremely convenient to write it with this notation. So again, it's a little uncomfortable, but just let it go. It's fine. It's not a problem. And then likewise for the other. Okay, so you can take derivatives of derivatives. Everybody happy with that so far? Okay, what does it mean geometrically? Now, let's think back to single variable calculus in Calc 1. If you take a derivative, we have a geometric interpretation. It tells you about the slopes of the tangent lines. That's how we think about it geometrically. Alternatively, we think of it as giving us the rate of change of the function. Okay, sure. Okay. Second derivatives in Calc 1. Concavity. Right? And you can justify thinking of it as concavity by, well, you can draw a picture like this, and if these slopes, right, what's happening to the slopes here? Here the slope is negative, here the slope is slightly positive, here the slope is quite positive. You can see that these slopes are increasing. Now, in making the determination that this is concave up from that, notice I'm combining two different points of view on derivatives. The first derivative I'm thinking of as giving me slopes. The second derivative, so the derivative that I'm taking of these derivatives, I'm viewing it not as slopes, I'm viewing it as rate of change. I'm viewing it as, okay, as I move in that direction, how are these slopes changing? Right, so using two different points of view on derivative. Okay, anyway, punchline, old news, second derivative addresses concavity. If the second derivative is positive, it's concave up. Right, if the second derivative is negative, it's concave down. All right. Okay, how does that apply in the multivariable context? Well, it's the first couple of bits here are kind of exactly what you would expect. Let's think about what is the partial with respect to y of partial of f with respect to y, if we're looking at a graph of f here. Well, partial with respect to y here says we're going to hold x constant. Right, so holding x constant means we're going to be looking in a, let me do this with the highlighter. We're going to be looking in a plane like that, and we're looking at that cross section in that plane where y is where x is constant, and then moving in the y direction. And so, no surprise. Notice very conveniently for both of these derivatives, both cases I'm holding x constant. So this entire calculation happens in that plane where I'm viewing z as a function of y, and it's effectively a Calc 1 problem, and no surprise, it works out the exact same way. If this second partial with respect to y is positive, then it means that these slopes, let's see, let me draw these. If you take the slopes of those cross sections, the slopes of these tangent lines, as you move in the y direction, these slopes are increasing. That means concave. Okay. And analogous exercise I'm going to leave for y'all to think about on your own. But if you are looking at the partial with respect to x of partial f with respect to x. Right? Well, now you're holding y constant. That means you're looking in, oh gosh, let's see if I can draw this. There we go. You're looking in a plane like that. Cross section that looks like that, and x is the only variable throughout this whole time. Y is constant for this entire calculation. Thus, we're in this plane where y is a constant throughout the whole calculation. We're just looking at that single variable cross section curve, and it's just the same. So think through the details and persuade yourself how that works. Here's where it gets weird, though. Let me rephrase that. Here's where it gets not analogous to single variable calculus. It's disappointing because familiar terms or familiar coincidences are always nice. But what if we were looking at the y partial of the x partial? You cannot just say, oh, this is just like single variable calculus. It's not. There is no single variable analog to what I'm about to show you here, because in I mean, critically, what happens in this phenomenon I'm about to show you is that there are two different variables that you're taking derivatives with respect to. So it's directly contradictory to the idea of a single variable function. So this is a brand new idea. Don't look for, oh yeah, this is just like in Calc 1, because it's not. What's hard is you can't just say, oh, look at a particular cross-section. I can't just say, oh, well, yeah, x is constant throughout this entire calculation. No, it's not. X is the variable for the first derivative that you take. Y is a constant for this first calculation, but wait a minute, y is not a constant over here. For the second half of the calculation, y is the variable, and x is constant. So this calculation does not happen in a single cross-section. Right? So the way we're going to make sense out of this, though, is just think it through one bit at a time. And these first derivatives I'm going to interpret as slopes of cross-sections. So here I've attempted to draw, for example, let's say this is a tangent line. Use your imagination. This is a tangent line in a plane parallel to the x-axis. Let's see if I can do a decent job. So there's a plane parallel to the x-axis. And notice I didn't draw the surface here because it makes the picture harder to sort of interpret. But imagine at that point, you look up, you look in this green cross-section plane, maybe this is the tangent line, and we can talk about what the slope of that tangent line is. But now ask, what happens to that slope not as we move in the direction that we were going. We're not moving in the x direction, right? We're moving in the y direction. So I want to look at these slopes of these tangent lines in planes that are like this, but moving that way. Does that make sense? So now this is my attempt to draw that. So I've got these various, at that point, and then over here, and then at that point. Right, I'm saying we've got these various different cross sections, and so let me do a hand wave. So imagine that my forearm here, right, represents that first tangent line. And now, as I move this way, my forearm starts tilting down. Right, so this is what we're trying to get a picture of. So this picture would be an example of how my x partials, which are positive to start off with, as I move in the y direction, my x partials are decreasing. So if this were negative, I would have something that looks kind of like this. Yeah? Y'all are too young to remember this used to be a dance move when I was in high school. Yeah. So this kind of so you just try to visualize now what is my forearm kind of tracing out here. So as I pull it back this way, imagine the kind of a surface that would be, right? So it's got that slope over there, but as you come this way, it does like that. And I appeal to your geometric intuition. It's like I had a sheet of rubber. Imagine a sheet of rubber that I'm holding at the four corners, like this, right? I have to kind of twist it this way to get the slopes positive on this side, but I have to kind of twist it the opposite way on the other side to get the slopes negative on that side. So it's like, imagine taking a sheet of rubber and putting a twist in it. Right? So what this detects, what this algebraic construction detects, geometrically, is a surface that has a twist in that sense. Does that make sense? It's you got to think it through. Look at the picture. Etc. By the way, what would happen if this expression were positive? Well, if it were positive, instead of larger values, instead of positive slopes turning into negative slopes, it'd be the other way. It'd be negative slopes turning into positive slopes, right? Like this. And so that would suggest that you're, instead of twisting it this way, that would just suggest you're twisting it the other way. Still a twist. Okay. So again, there is no single variable analog of this. Okay. Okay, I've only got, oh, no, I don't either. So very quickly, though, this neat theorem here, it turns out that if you are looking at second partial, mixed second partials, such as we were just discussing, it turns out that most of the time, in some sense, it doesn't matter which order you take the partial. So if you take the y partial of the x partial, or if you take the x partial of the y partial, you're very often going to get the same answer. The only constraint is you need for the second partials to all be continuous. And again, very often that's the case. Look back at this example here where we computed a bunch of partials. These second partials are all continuous functions. They're all polynomials. And that's why, and you might not have noticed this as it happened, but these mixed partials were the same. The y partial of the x partial, the x partial of the y partial, same thing. So it's not always true for sufficiently irregular functions. It's not true, but it's true for all polynomials. And more generally, as long as your second partials are all continuous, the mixed second partials are always equal. Okay, great. So we've just finished section 4.5. We're now officially caught up. I always front load the schedule a little bit so that it's a way of lighting a fire under myself, make us move faster. But we're now caught up, and okay. See y'all later. So quick comments about the exam. The exam, as you know, is tomorrow. I sent y'all an email about the content. That's fair game, so that remains. So about the homework that is assigned for today, I think it'd be very reasonable to not start on it just yet, right? Because y'all got an exam to study for. This material that we talked about today is not even on it, right? So don't start it yet, right? So I would suggest that you delay the stuff that we talked about today. Don't start on those homework assignments until after tomorrow's exam. And that's Wednesday, and I believe I have it set up on the schedule that homework assignment's not due till Friday anyway. So that should work out nicely. Okay, all right, see y'all later.